Welcome to qnawire.
We have this large turntable here, and a person is walking on it, and it says you are walking on it, barefooted, nonetheless. Um, and you start at the rim and you walk inwards, and you walk slowly towards the center along a radial line painted on the surface of the turntable. Our mass is 70 kilograms. Um, the Let's see here. The Initially, this turntable is going as a period. It takes 8 seconds to go around one time, to make one revolution. And let's see here. What else have I had here? And 6 meters diameter. So, and they ask us how if we get to 3 meters here, if we get halfway in towards the center and we start to slip, what is the coefficient of friction between our bare feet and this platform? So if we look from a top-down view here, we just have our I'm going to call this plus here. So we have our centrifugal acceleration is in towards the center, towards the radius axis of rotation, which means our friction force has to be in to keep us from sliding off. And then if we look at ourselves from the side, we have our weight, the normal force, and the friction force. Now, the angular velocity, if the period is 8 seconds, is pi over 4 radians per second. Our initial position here is the outer radius of the disk, and then we end up at R1 equals 3 meters. So let's see here. We're told that the mass moment of inertia of the turntable is 1,200 kilogram meters squared. So we can find the mass moment of the total system in the initial state when we're standing out here at the edge, and that is just 3,720 kilogram meters squared. And then we can find the mass moment when we're out, have moved into 3 meters from the axis, and that winds up being 1,830 kilogram meters squared. Now, we're assuming that our friction force at this point, when we start to slip, the friction force is a maximum, so it's the static coefficient of friction times the normal force. The normal force is just our weight. And then a force balance here says that the friction force has to be the mass times our acceleration at this when we're at this point. So it's our mass times R1 times omega 1 squared. So now we need to figure out what omega 1 is, so that we can solve for mu s. So omega 1, because we're walking on along a radial line here, there's no torques acting. There's no net torque acting about this axis of rotation. So we have momentum conserved. So we have, let's see here, we have the initial momentum is our initial mass moment times our initial angular velocity, and that equals our momentum in the second state, which is the second J1 times omega 1. Which just says omega 1 is J naught over J1 times omega naught. Well, our static coefficient of friction is R1 times omega 1 squared over G from here. We can substitute omega 1 in to there, and we get R1 over G times the ratio of the mass moment squared times the initial angular velocity squared. And we have all of these values, and we can plug everything in, and we get that 0.780. So we can kind of take a look at some of these values. If as R1 goes up, so that's where the radius where we start to slip, that it turns out that let's see here. As R1 goes up, basically the static coefficient of friction goes up. So yeah, that because our angular, well, it's kind of an interesting problem here because it's not quite that clear, right? Because we have R1 here too, so that's changing this. So, and because we have, if JT were 0, which is not, really a good approximation given that it's, a significant portion of the total. That then you could see that in fact you would have R1 in the denominator, right? Because you'd have R1 squared down here, or you'd have R1 to the 4th. So basically, that's a bad that's a bad check, because it doesn't make any sense that you slip out if this needed to be higher to keep your from slipping out at the end, then well, you would slip immediately. But in fact, if you were actually to plug in, say, a smaller value for, let's see here, if you were actually to plug in, say, 2 meters here, well, this thing would go down substantially, and this thing would go up a little bit, but then this thing would go down very substantially, so this thing would go down. So that's a bad check. But again, you can kind of see that this thing makes sense. If omega naught is 0, well, then we get basically this isn't spinning, so then, this, if we're going to slip and it's not even spinning, then the static coefficient of friction is going to be 0 because we're going to slip no matter what.